shall we, Benny, are you ready to present?
Yep, I'm ready. Thanks, Julian. That was awesome. Yeah. All right, I passed the little presenter ball to you. Thank you. So don't mute yourself yet so you can tell me if you can see my screen. Yeah, you can see it? Yep, all right. I'll mute myself now. Fantastic. All right, thanks everyone. Thanks, Craig, for the opportunity to talk about some of the work that I did during my PhD with collaborators at UMass and that I'm continuing to do as a postdoc fellow here at Lamont. I work on ice sheet modeling. We care about ice sheet models because they're the primary tool that we use to predict how sea level will change in the coming decades and centuries. These are two examples of inundation scenarios for the next century, one for the Bay Area, one for Thailand. But what's important to note is that things like sea level rise become a sort of multiplier when we're facing other sorts of drivers of displacement and difficult global situations like what we're going through today. We know that sea levels are rising because the ice sheets on Greenland and Antarctica are both melting. In Greenland, the change that we've seen is quite dramatic over the period of this NASA animation. The Greenland ice sheet has contributed about 1 centimeter to global sea level, and that its yearly contribution is accelerating. So for as long as we've been able to see it from space, it's been losing mass, and this motivates us to try to understand better when in the past these sort of changes have happened and how the ice sheet responds in an equilibrium sense to past warm climates. So geologists have worked on this problem for a long time, and this is a compilation of what we think happened to global sea level in response to other periods in Earth's history that were naturally warmer than today due to different orbital configurations as well as different concentrations of atmospheric CO2. And, this is showing 4 different periods: the present day, the Eemian, 125,000 years ago, marine isotope stage 11, 400,000 years ago, and the warm Pliocene, 3 million years ago, which you can see have sometimes different concentrations of CO2, generally relatively modest global temperature perturbations above modern, but quite large responses from our ice sheet. Unfortunately, the most uncertain part of this whole effort to reconstruct past sea level is knowing where the contributions came from, whether they came from Greenland or Antarctica. And so that's the essential question that's kind of driving this research is, can we get a better understanding of when Greenland specifically contributed to past sea level and how much ice did it lose? And in that sense, we can actually answer both questions because these are sort of the 2 main contributors to these large sea level heights. In order to get an understanding of glacial history in the past, a commonly used tool that I'm going to talk about leveraging today is cosmogenic isotopes. There are a number of people at Lamont that work on these, but essentially the way that they work is when you have a glacier that covers a bedrock surface, it's being constantly bombarded by cosmic rays from space, which can lead to chemical reactions within certain minerals that accumulate over time. And so when a glacier retreats, you have this spallation occurring on bedrock, and this starts what we call a cosmogenic clock, with regions that became ice-free earlier having a higher concentration of these cosmogenic nuclides than regions that became ice-free recently. This method is especially powerful for telling us the last time that a landscape that is currently deglaciated was covered by ice. It gives us a sense of when the ice retreated from that location. But there's a recent observation that has forced us to start thinking about how these nuclides operate in more complex situations. So Jörg Schaefer, who is one of my mentors at Lamont, put out a paper in 2016 where they were able to measure these same cosmogenic nuclides, which only accumulate when the ice is gone, but from beneath the part of the ice sheet where the thickest ice is today, the summit of the ice sheet. So this was a rock core that was recovered along with the ice core drilling operation that happened in central Greenland in the early 1990s. But this was the first time that this cosmogenic nuclide approach had been applied to the rock core, and they expected if the ice sheet had been stable over the last few million years, to find very little of these cosmogenic nuclei. But instead, they found quite high concentration. And they suggested a number of different scenarios for what could have given you the observations that they had from beneath the ice sheet. So this is showing in the blue and red bars proposed times of ice cover in blue and ice-free conditions in red for 3 different scenarios compared to the global benthic delta 18O stack, which is the line that goes off the bottom. This global benthic stack is a measurement of oxygen isotopes made on deep sea benthic foraminifera, an organism that lives on the seafloor, and they record the oxygen isotope composition of seawater in their shells. So this record can be thought of as an integrated record of global climate over the last 2.5 million years. So what Jurg and others did at this time was they tried to propose different scenarios that are related to this benthic climate record. But the interesting thing here is that these different scenarios predict very different levels of stability for the Greenland ice sheet. On one case, being completely stable for the last 1.1 million years, and another case, essentially having a substantial retreat every time the Earth is in a relatively warm climate state. So me, as an ice sheet modeler, I wanted to try to understand whether we could use ice sheet models to get a more realistic, physically based understanding of when the ice sheet may have been more or less stable and what would have driven that. That benthic oxygen isotope record is really good for understanding long-term climate evolution, but we know that it also leaves out a lot of information. It comes from the deep sea. There are secondary effects from temperature, which are difficult to deconvolve from the signal. And so what we've done in this work is we've developed and relied on long climate records that we think are more relevant for understanding Greenland temperature evolution and that also cover this time period of interest. And so I'm going to talk about models that we've forced with 2 different climate reconstructions. One comes from Lake Elgagitkin, which is a crater lake in northeast Siberia, where my colleagues at UMass have developed a 3.6 million year climate reconstruction that's shown in the orange circle. And another is from an International Ocean Discovery Program, Site 982, the green circle just off the southeast coast of Greenland. In purple on this plot on the left is the Greenland temperature reconstruction. And then that same benthic oxygen isotope is shown at the top with CO2 at the bottom just for comparison. And what we can see is that we know that Greenland temperature has a lot more short-term variability than what we see in the benthic oxygen isotope stack. So we think that by using these 2 records that are both closer geographically and have higher resolution, we're representing something that's closer to the actual temperature signal that Greenland would have been receiving over the last couple million years. And the benefit of both these records is they actually extend over the time period of interest. You can see here, compared with the benthic oxygen isotope stack, going back more than 2.5 million years, we also have high resolution reconstructions of this terrestrial temperature from a crater lake in Siberia and sea surface temperature from the North Atlantic. And so I'm going to use these records to drive the ice sheet model. Our modeling approach is I run a 3-dimensional thermodynamic ice sheet model that was built by Dave Pollard and Rob DeCanto at Penn State. Rob is at UMass now, Dave's at Penn State. It's a hybrid shallow ice, shallow shelf model where we couple 2 different domains that allow us to make some assumptions in order to make the model more computationally efficient. We couple those domains using a parameterization for how ice moves from the grounded part where it's sitting in areas where the ice is floating on water. The model includes ocean melting, calving, and basal sliding so that we can capture ice dynamics. In order to develop the climate forcing, we're going to use these proxy records to understand how climate has changed through time, but we also need a sense for the spatial distribution of temperature and precipitation to run the ice sheet model. So Julian already introduced the RACMO reanalysis product, which is sort of our gold. Did someone have a question? Okay, I'm going to keep going. I just heard something. now is sort of our gold standard for temperature and precipitation products on both of the ice sheets in Greenland and Antarctica. We actually use our different regional climate model called REGCM3, which we've coupled to a global climate model. And the benefit of that is that we can run the model under very different boundary conditions, like what we would have seen in the geologic past. Shown on the right is just a comparison between our model and RACMO for present day. We use RACMO as sort of a tuning target to get the general structure of the temperature field as well as the precipitation field on Greenland. Note that our climate model, which is the far right column, is relatively wetter compared to RACMO, so that leads to a greater ice sheet stability in some areas. These are receiving more precipitation, but the main structure of the known precipitation field, for example, high precipitation in the southeast, generally higher precipitation up the west coast, and a very arid northeast is captured by our approach. And the benefit of this approach, as I was alluding to, is that we're able to model what the climate would have been like for very different Greenland scenarios, which we think we had in the past and which we're trying to understand with reference to these cosmogenic isotope records from the bottom of the ice sheet. We can model what climate would have been for very large ice sheets, like what we may have had during the last glacial maximum. We can also model what climate would have looked like for smaller ice sheets that are either partially retreated or nearly completely deglaciated. Finally, in order to bring these two things together, what I've done is run an ensemble of ice sheet model simulation where we force the model using linear interpolation that's driven in time by these proxy records, but allows us to select a number of different spatial climatologies, going from less deglaciated to more deglaciated, and comparing the results against the observations from cosmogenic nuclides at the base of the Greenland ice sheet. In order to sort of make a more direct comparison, the last thing that we need to recognize is that while we understand quite well this simple case of exposure in terms of interpreting cosmogenic nuclides, that the ice sheet simply retreated and we can measure the last time that the area was covered, in this central Greenland area, the ice sheet history is a lot more complex. We're very likely dealing with multiple periods of ice sheet retreat and advance. And so in order to do our best job of treating that, we've also included a subglacial erosion scheme. It's a simple erosion scheme that's based on the hardness of the bedrock, the speed at which the ice is sliding, and excellence. And this recognizes that this production of cosmogenic nuclides, it doesn't just happen at the very surface of the rock, it happens throughout the bedrock column in an exponentially decaying sense. And so we've incorporated all of these things into our modeling framework. And the way that this works is we run these ice sheet models, we predict how the cosmogenic nuclides accumulate in the bed. So these accumulate when the area is ice-free, and they start to decay when the area becomes ice-covered again. And you can see in the Northeast, for example, in areas where we have fast sliding ice, we lose a lot of these nuclides through erosion. Finally, at the end of the simulation, we select the spot underneath the summit where we have data, and we calculate the misfit between what we've modeled and what we've measured. And these are the results of some ensembles of simulations. So we have these two different proxy records that we've run ensembles with. On the left-hand side, terrestrial record from Lake Elgin-Gitkin. On the right-hand side, this SFT record. So we have these 2 degrees of freedom, one essentially describing the threshold in the proxy records for when we have deglaciation or a warm climate, and the other describing how warm that climate is, how much of the ice sheet is retreated. And you can see that there's a lot of options for producing the observation that we have beneath the ice sheet, but this allows us to more realistically select n-member scenarios that describe the ice sheet evolution over the past 3 million years. And you can see also that there are a lot more scenarios using this terrestrial climate record from Lake Elgin-Gitkin, which are able to fit the data. If we do the sort of same analysis that Jörg did in that 2016 Nature paper, we're able to see the timing when we think the Greenland ice sheet retreated and provide some sort of end-member scenarios on its stability. And sort of at first glance, you can see that depending on which of these proxy records we use, we get really different answers for how stable the ice sheet has been over the last 3 million years and when it most likely collapsed. There are some similarities between both of these methods that we see likely ice sheet collapse during marine isotope stage 61, for example, but there are also differences. You can see highlighted in those boxes in isotope stages 53 and 49. And finally, if we just zoom in on the last million years, like I mentioned before, there's this one scenario where we essentially have a very stable ice sheet for the last 1 million years. And we find that we can recreate that behavior. That scenario is realistic, but only if we use this temperature record from the North Atlantic. Has fewer ways to capture the data that we see at the base of the ice sheet today, whereas the Lake Elgin-driven record indicates that there have likely been ice sheet collapses over the last million years in response to global warming. So I'll wrap up in for the sake of time what the combination of icy models and subglacial records of cosmogenic isotopes allow us to provide more realistic scenarios for how stable the Greenland ice sheet has been over the last 3 million years, and allow us to generate testable hypotheses where we can go to other places and say which scenarios, which we now think are sort of physically motivated, are most consistent with the data from other areas. And that's one of the things I'm working on at Lamont, so I'll just give a little teaser. Because we're calculating erosion, we're able to use these cosmogenic isotopes as tracers, here showing the concentration of nuclides that are delivered in sediment material that makes it to the coast. And what we hope this will allow us to do is, here an example just zooming in on the last 800,000 years, compare with offshore records of these same proxies, so we can get a sense for how to constrain the model, not just from beneath it, but also from records that are being developed around it. So I am working at Lamont to further develop our ability to use marine records, offshore records, as a constraint on icy model behavior. And then lastly, you may have seen in Science Magazine, in addition to this observation from beneath Summit, there was recently discovered in a freezer in Denmark some sediment from Camp Century, another ice core that was drilled in the 1960s, which is now being analyzed for these isotopes. And as you can see from one of these ensemble examples, the extent to which these two samples are different or similar is going to give us a lot more power to constrain what the ice sheet model does through time. So with that, I will wrap up. Say thank you again to my collaborators and funding from the NSF, and I'm happy to take the questions.